Rates of reaction is a big and important topic about which we'll do a lot next year. For the moment this year, it's really a fairly gentle introduction to the subject that you need. First of all, you need to be able to suggest ways of measuring rates of reaction. And obviously the way you do that depends on what reaction you're talking about. So, for example, if you were looking at a reaction of a metal dissolving in acid, like this, there would be various things you could do which would let you monitor the progress and generate actual numbers so that you could quantify the rate of reaction. An obvious one would be that the gas is produced in the reaction, and you could measure the volume of gas that was produced, so you could then generate a graph of the volume of gas as a function of time. And that is the sort of thing that you're aiming to do in a rates of reaction experiment. So you would need to be able to describe equipment in which you could do that. So for example, you could have a flask like this and a delivery tube coming out, which might be connected to a gas syringe. A gas syringe is like a normal syringe, but it glides very smoothly so that the gas remains at atmospheric pressure rather than sort of pressure building up and then jerking as would happen with a normal syringe. So this would be your gas syringe here, and this would be a reasonable way to follow the rate of reaction. When you draw things like this, you obviously have to draw it carefully and make sure it would work. If you didn't draw the bung in the top there, then it wouldn't work, because obviously the gas wouldn't all go through the tube, it would just come out the top here and you wouldn't get any results. So although these are simple ideas, you have to be careful with the drawing, and as always with drawings you have to label them and make sure you say this is a gas syringe. And also you have to state the size of equipment that you're using when you get asked questions like this. So you would obviously need to calculate roughly how much hydrogen you'd expect. So if you work out how many moles of magnesium are reacting, you can estimate the volume of hydrogen, and if it's less than 100 cm cubed, then you could use a 100 cm cubed one. If it was a bigger volume, you'd need a bigger syringe, and so on. And your reaction mixture would be in here, so label this as a conical flask. And again, put the size on there, so 250 cm cubed or whatever. So just simple questions like that are quite common, where you just have to suggest a sensible setup. You also can see, I think, that there's a sort of potential flaw with this experiment, which is that you've got your magnesium, which is a solid, and it's got to be added to the acid to start the reaction going. And obviously, in order to get the magnesium in there, you'd think, well, I'll have to take the bung out, lob the magnesium in, and then very quickly put the bung in place and start collecting the gas. And that's fine so long as the reaction's pretty slow, but if the reaction's fast, then you might lose a significant amount of gas during that delay between putting the magnesium in and getting the bung in place. So it's also just worth thinking about ways you could get around these problems, because they just might ask you to suggest something like that. So you could, for example, do something like this, where you put your acid ready to react in the flask, and instead of just putting the magnesium in, you could put the magnesium in a boat floating on the acid like that, so that they're both in the flask but they're not yet mixed together, so no reaction's going to happen. You can then put your bung in place ready, and then you simply capsize the boat, shake it or agitate it slightly so that the magnesium drops into the solution and start the reaction, and then there's no loss of gas. So it's just worth being aware of sort of tricks like that you could propose to use. There are other ways you could follow this reaction. Another thing that's going to happen is that there's going to be a change in the mass of the stuff in the flask. So a very easy way to do it, in principle, would be to do it on top of a balance. Okay, so if you just do it on top of a balance like this, so right, here's a balance, here's your reaction mixture, and you just let the gas escape into the air, and obviously as it does that, the mass decreases. And so then, instead of having a volume of gas as a function of time, you could have the mass as a function of time and follow the progress of the reaction that way. Or you could say, well, the pH is going to change because we're adding acid, but the acid's being neutralized, so you could follow the pH as a function of time. That would also be a possibility. So what you get out of experiments like this is some kind of graph. So let's now start to talk about graphs. So let's suppose that you've got to plot a graph of volume of gas versus time. It's possible you could be asked to do this in an exam. They could give you some data in a table and ask you to turn it into a graph. So if this is your page, it's very important that you choose sensible scales. So if they give you some graph paper and ask you to put your own scales on, what you don't want, is a little graph up here on a big page of graph paper. That's not sensible choice of scales. So what you have to aim at is to make the graph as big as you can whilst choosing sensible scales. And sensible means things like, if the volume of gas is measured in cm cubed, you don't want 1 square equals 6.3 cm cubed or something, because that's obviously silly. You're going to make mistakes if you do things like that. But don't use 1 square equals 20 cm cubed if 1 square equals 10 cm cubed would fit in. That's what we're saying, is make the graph as big as possible. So hopefully it will take up a sizable portion of your page. Make sure you label the axes properly, so put all the numbers on there. So this might be time in minutes. You must make sure you label the units you're using, so not just time, but time/minutes or seconds or whatever it is. So 1, 2, 3, 4, 5, whatever. And up here, this is going to be volume of gas, and again put the units on there. So that might be cm cubed, for example, and again label it clearly. And when you plot the points, you've got to do them carefully. They will check that you've got them in the right places, so don't rush that. Just check that they've on the right place on the grid when you mark your points on, and mark them with X's are better than dots, because the center of the X is a more precise sort of thing. Okay, so you might have something like that that you can plot, and then you would have to draw some kind of curve through that, because that obviously isn't a straight line. So you have to make your best effort at drawing a smooth curve. That doesn't mean drawing lots of little straight lines connecting the points. Okay, that's not what they want you to do. If they ask you to fit a curve to that, it means that you've got to do your best to fit a smooth curve. It's actually really hard to do on the board. It's easier on paper because you can kind of swing your arm through a curve. But I'll just do my best on here. Okay, that's not too bad, but you can see it's not as smooth as all that. Make it as smooth as you can when you do that. So that gives you a graph that shows you the progress of the reaction. Now the rate of the reaction is the gradient of that curve. It's how steep that curve is at any given point. And you can see that's not a constant, because it's steep at the beginning and it gets progressively less steep as the reaction proceeds, and at the end we just about reached it. But in reality, of course, if we let it go on for long enough, it's going to level off completely like that. So it goes from being steep at the beginning to being flat at the end. So you can't say the rate of reaction is and just put a number on it, because the rate of reaction is constantly changing. So what you have to do is to decide when you want to know the rate of reaction. Do you want to know the rate after 2 minutes or 5 minutes or what? And then what you do is you plot a tangent to the curve at that particular point. So suppose we want to know what the rate is at 3 minutes. Okay, so here's the 3-minute point on the curve. And what we mean by a tangent is a straight line which just touches the curve at that point. Tangent drawing is not a particularly easy thing to do well, but what you're aiming to do is to take a straight edge, the ruler or something, and fiddle around so that it's just about touching the curve at that point. Once you've got that, then you can draw on your tangent. So you're going to draw something that looks a bit like that. Okay, so it's just touching the curve at that point, and you can see the idea is that that's the point it touches, not up here, not up there. Now they give you a fair amount of leeway with tangents, so don't sort of spend 3 hours trying to get it right, but it needs to be reasonable, so if that's your curve and your attempt at a tangent sort of is something like that, so it's clearly not just touching the curve at a point, they're not going to accept that. Equally, if you do it so it doesn't touch the curve at all, like that, they're not going to accept that. So you've got to make sure it's just touching the curve at a point, and you've got to make sure it's the right point. So if this is the point at which it's meant to be the tangent, they're not going to accept it if it looks sort of like that. So that yes, it's a tangent to the curve, but it's at the wrong point. Okay, so it's something you do need to practice. The other thing that's worth saying is that when you draw your tangent, you should make it as long as you can, going right the way across the page like that. What people quite often do is, they get their curve like this, and they say, right, I'm just going to draw a little tiny tangent. So they draw something, like that. And that's a bad idea, because what you're going to be doing is measuring the gradient of that tangent, and the longer you draw it, the more precisely, the more accurately you're going to be able to measure the gradient. So let's have no little tangents like that. You've got to do the whole width of the page like that. So the rate of reaction at 3 minutes, which is what we would have been asked to measure if this is what we were doing, rate of reaction after 3 minutes is the gradient of that tangent. Okay, so that's what you need to remember. If you're asked to figure out a rate of reaction from data like this, you must draw a tangent and then you measure the gradient. What does a gradient mean? Well, it means the vertical change divided by the horizontal change. So what you would do would be to draw a triangle, and as I say, the bigger the triangle, the better. So if you've got this on graph paper, it's obviously much easier than it is here, but you're going to have some kind of line going across like that, and you say that is the change in volume, and this is the change in time. And the gradient is equal to delta volume over delta time. Okay, so that's how you quantify the rate of reaction. So you need to practice drawing tangents, and you need to remember how to calculate the gradient. It's the vertical change, which in this case is change in volume, divided by the horizontal change, which is change in time. So in this case, that might be something like, I don't know, say 52 minus 14. And the thing to do is write down the raw numbers, because it minimises your chance of error if you do that. So let's say that's 52 minus 14 is the change in volume. If you know, that's 52 there and it's 14 there, and the change in time might, you know, is 7 minus 0. And the advantage of that is that you're less likely to make slips. So that's 38 over 7, and that comes to 5.4. But the important question is 5.4 what? There's got to be a unit here to express what the rate of reaction is. And the key to that comes from the way it was calculated, because the volume that went in here was in cm cubed and the time was in minutes. And so the units are cm cubed divided by minutes. And you write that as cm cubed, and remember, when you divide by something it becomes a negative power. So it's cm cubed minute to the minus 1. And that's the rate of reaction at 3 minutes. If we'd done that at an earlier time, the gradient would have been steeper, so you'd have got a bigger number for the rate of reaction. And if we'd done it at a later time, it would have been smaller. And at the end of the reaction, obviously it would have been 0 when we'd reached the end and no further change was taking place. If we had followed the same reaction by measuring the decrease in mass as the hydrogen gas escapes from the flask out into the air, then again we'd have got a curve, except this time, because the mass is decreasing, we'd have got a curve that looked something like that. Again, levelling off at the end when there's no more hydrogen to be lost. And you would just find the rate in exactly the same way. Draw a tangent at whatever time you want to, measure the gradient of the tangent, and the units this time, instead of cm cubed per minute, would have been grams per minute. So you'd have written it as grams per minute like that. One thing that you're quite often asked for in rates of reaction questions is the initial rate of reaction. Now, initial means at the beginning. So you just do that in the same way, but this time you have to try and draw a tangent that just touches the curve right at the very start. That's actually harder to do, but again, they'll probably be correspondingly more lenient about getting it, about what number you get. So you try and draw a tangent like this that just touches the curve at the beginning. Something like that. And the gradient of that, which remember is change in mass, which is that, divided by the change in time, which is that. Okay, so the rate, the initial rate, which means at the beginning, is delta mass over delta time in grams per minute. So, as far as we're concerned at the moment, you can express rate of reaction in terms of any variable that's convenient to measure. Next year, when we get more immersed in the sort of theory of rates of reaction, this variable will almost always be concentration. And so the unit then, if it's concentration that's changing here, will be moles per dm cubed per minute. But for the moment, that's just one of the many possibilities that we've got to consider. One thing you may have to do is to sketch or interpret curves relating to similar experiments but done under slightly different conditions. And so it's important to make sure you know what you're looking for there. So if we take one of these gas volume experiments, so we've got gas volume produced in whatever unit, let's say cm cubed, as a function of time in seconds or minutes, whatever we're measuring it in. And we might say, right, okay, this is our first experiment. Okay, so the usual thing that it levels off when it's all over. Now let's ask the question, what happens if we repeat the experiment but at a lower temperature? Well, you know that when the temperature is lower, the rate of reaction in general will be slower. We'll talk much more about why that is a bit later on, but for the moment let's just use that fact and say, what difference does that make? Well, remember that the rate of reaction is the gradient of the curve. So what that means is that the curve is going to be less steep at a lower temperature. But in the end, if we've got the same amount of substance reacting, we'll get the same amount of product. It'll just take longer. So what we would get then is something like this. Okay, so this would be lower temperature. And the two important features of it are that you get a slower rate, which therefore means that it's a less steep gradient. And you can see that's true at all points. Okay, it's always less steep than the one at the higher temperature. But on the other hand, the final volume is the same, you know, if the same amount of reactants are used. And that's important, so you can see what the curve should look like, and you can see why that makes sense. Okay, so that's a first case. So now let's think about a different case. Okay, so this is our second situation. So this is the reaction, remember, that we were following, but it could be any reaction. And let's just be a bit more specific this time and say, right, this is going to be an excess, so we've got enough magnesium to react with however much acid we throw at it. But let's say that this is half the original concentration. Okay, so we're repeating the experiment with, you know, maybe 1 mole per dm cubed instead of 2 mole per dm cubed or whatever, but the same volume of HCl. Now there are two things here that are important. The first is that we've reduced the concentration, and the concentration is going to affect the rate. But the second is that, remember, moles is concentration times volume in dm cubed. So if we've got the same volume but only half the concentration, we'll only have half the original moles. So we've got two differences here that we've got to worry about. The first is that we've only got half the amount of acid reacting, and that's obviously going to mean that we only get half as much product. And that means that in the end, we're going to end up here somewhere rather than there, because we're only going to get half as much gas being produced. But the second is that the concentration is lower. Decrease in concentration in general will decrease the rate of reaction. Again, we'll talk about why that is in a bit, but that's the general principle. So what we expect is that the rate of reaction will be lower, and this time in the end you'll only get half as much product. So what we're going to get is something like that. Okay, so we've got a less steep curve, lower rate of reaction, because that's the effect of lower concentration, but also this time because there's going to be less product produced. That's reflected in the graph because it only produces half as much gas in the end when the reaction is all over.